For the past decade, AI progress has followed a familiar playbook: bigger data sets, wider models, more parameters. This paper argues something different, that one of the biggest untapped levers in reinforcement learning wasn't width, it was depth, and once you unlock it, entirely new agent capabilities emerge. While vision and language models scaled to hundreds of layers, reinforcement learning mostly stayed shallow, often just 2 to 5 layers deep. Not because deeper models weren't useful, but because they were considered too unstable to train. This paper challenges that assumption directly. The authors mentioned that it was a combination of three ideas: self-supervised reinforcement learning, massive data throughput from fast simulators, and radically deeper stabilized architectures. Together, these three helped finally make deep RL viable. A key architectural insight in this paper is that instead of forcing every layer to learn something new, deep networks refine behavior gradually. Residual connections allow each layer to make small improvements, preserving information and stabilizing training, even across hundreds or thousands of layers. Depth becomes a strength, not a liability. One of the most striking results is that performance doesn't improve smoothly. As depth increases, agents hit critical thresholds, points where capability suddenly jumps. For example, at 64 layers in some tasks, performance explodes. This is classic emergent behavior. Beyond metrics, the qualitative changes matter even more. Shallow agents brute force their way towards goals. Deep agents learn entirely new strategies. In humanoid tasks, for example, deep agents learn to vault obstacles, a behavior that never appears in shallow models. This isn't tuning, it's new skill formation. Depth enables agents to reason over long horizons. Instead of reacting step by step, deep agents learn internal representations that encode environment structure, like navigating around obstacles instead of straight toward a goal. This unlocks tasks that were previously out of reach. Another subtle insight is that deep agents can stitch together experiences. They reuse partial trajectories learned during training to solve new configurations at evaluation time, reduces reliance on exhaustive data, and improves robustness in unseen circumstances. The paper shows that depth creates richer internal representations of the world. Deep embeddings focus capacity on goal-relevant states. Better representations lead to better exploration, which produces better data, which further improves learning. A virtuous cycle emerges. The exciting potential of this paper is that depth-scaled RL could become a building block for embodied robotics, logistics and planning systems, self-improving software agents, hybrid systems combining LLM reasoning with RL action, and so much more. The scaling ceiling for reinforcement learning has been shattered, and this so makes it so exciting. And the result is a step change in capability, efficiency, and reliability. Check out the paper in the description below, and thank you for watching.